Hey, today we're going to talk about 9.5, global climate change. So take a moment, check out the enduring understanding, look at the learning objective, pause the video, squint your eyes, and look at all that essential knowledge. Set up your Cornell notes. So this topic of global climate change is kind of one of the most important topics that we will discuss this entire year. It is one of the topics that we have been kind of working towards, and we only have a couple more concepts left. But this is basically one of the biggest ones that we will discuss all year. So let's start. We have Milankovitch cycles. Milankovitch cycles are cyclical trends in the Earth's obliquity and eccentricity. Obliquity is our average or our axis angle, whether it's 22 to 24 and a half degrees. And eccentricity is the shape of our orbit, whether it is more of a circle or more of an oval shape. Now these cycles are in, like the obliquity cycle is 41,000 years, eccentricity is 100,000 years. You don't have to know either one of these. All that you should really pay attention to is that what happens throughout the Earth's history is there's times when we're going to be angled towards the sun and closer to the sun. So that should theoretically be a warming time in the Earth's climate. And then there should be times when we're angled away from the sun and we're farther away from the sun, and that should theoretically be a colder time. Now, this is something that scientists can calculate, and they can compare our geographical location to the actual climate data that we have. So Milankovitch cycles is part of this process to kind of piece together the history of Earth's climate. Because we didn't have thermometers 150,000 years ago, 800,000 years ago, 10 million years ago, but we do have other means of getting data. So we can look at historical data from the Earth's orbit around the sun, but we can also look at other data. So one thing that scientists can do is we can obtain ocean sediments, and we can analyze them for organisms known as foraminifera. So foraminifera are tiny little zooplankton, which means they are small animal-like floating organisms that are microscopic, and they form calcium carbonate shells, but each species has a different range of tolerance. So based on the foraminifera that are present in these ocean sediments, and these ocean sediments, you can see them right here. It's basically like the lines, like you might have darker areas and lighter areas, much like the rings on a tree. So you can analyze those for the different types of species that are present, and you can determine environmental conditions around that same time. Now, how do we do this? Because we understand the different species of foraminifera, and we know what types of environmental conditions they prefer. So for example, I'm just making this up, but like in a darker stripe, it might have species A of foraminifera, and they prefer warmer temperatures. And there might be this lighter stripe, and that might be foraminifera that preferred lower carbon dioxide levels, and so on and so forth. But basically, we compare the species that are present in these ocean sediments with species that we know now, and we will make a correlation between them, and that's how we will analyze this data. But we don't stop here. We'll also correlate this data with the Milankovitch cycles to see if there are certain trends. But we also don't stop here. We also can look at polar ice cores. So over, like every year, a little bit new ice gets deposited on, in Antarctica, and over hundreds of thousands of years, you have like a mile or a kilometer at least of ice. Actually, it's a mile of ice on Antarctica, and they take these giant drills and they bore out this giant ice core that's several 100,000 years old. So inside this ice core, they can find things like oxygen and carbon dioxide in little air bubbles. They can also look for dust that was deposited. So dust can be deposited from different parts of the world, and you can determine what the environmental conditions were based on different isotopes that are present. So you can analyze the carbon dioxide. You can determine the parts per million of carbon dioxide historically based on what's present in the air bubbles. But also in the air bubbles there was different isotopes of oxygen, and oxygen 16 is the normal isotope. But during warmer temperatures and warmer global temperatures, oxygen 18 is a very common isotope. So you will analyze those air bubbles, and if there's a lot of oxygen 18, you can make a correlation between oxygen 18 and global temperatures. But then you will also take that data and you'll compare it with the other data that we've determined from the ocean sediments and also from the Milankovitch cycles. So then what scientists do is they put all of this stuff together and they get this amazing piece of climate data. And this is the historical data from the Milankovitch cycles. So this is going to tell you whether you're close to or far away from the sun and what the angle is. I am not an earth scientist, so I don't know how to interpret that. So I'm just going to pretend that I understand that. I don't know. But what I do know is I can analyze this data right here where it talks about the change in temperature. So this would be, 0 would be like a normal or the standard global temperature or the average. And then if it's below or above, like if the temperature change is lower than normal, the temperature change is higher than normal. So if you notice, we have areas where it's warmer, we have areas where it's colder. I noticed that, about 100,000, just over 100,000 years ago, temperature got cold. And then it got really cold until about 10,000 years ago. Well, what happened 10,000 years ago? The end of the last ice age. So we had the retreat of the last glaciation, and we entered a warming period in the Earth's history. Now, how do we know that? Well, because we're looking at these ice cores. Now, this is not, we don't have thermometers, so we can't actually determine the exact temperature. However, we can correlate this temperature with other factors, like, for example, those ocean sediments, and also analyzing the oxygen isotopes. So there are different things that we can do where scientists can actually make these predictions and say, yes, these are the actual temperatures, historically speaking, over the last 800,000 years. That's how far back this goes. So another thing we can do is we can look at the CO2, because the CO2 was actually present and you can physically measure that in those ice cores. So this CO2 parts per million kind of hovered, between 200 and 250. There was a couple times it went up, and then if you notice, it's gone way up. So we haven't seen carbon dioxide this high in pretty much the last million years. And it's gone way up, like it looks like it should be going up, because if you notice here, now I want to show you something. We have this area, the high temperature, the high CO2, the high Milankovitch cycle, and then if you notice that Milankovitch went down, but this temperature kept going up and the CO2 kept going up. So there is something a little bit off here. This CO2 has gone up. So I'm thinking, and this is what scientists are thinking, that carbon dioxide is probably the cause of our temperature increases. As you look back throughout the historical data, like the peaks and the valleys are pretty much comparable throughout the last 800,000 years. And then they both kind of shoot up. And this one shot up a lot, and this one hasn't shot up as much as the carbon dioxide has gone up. Now, the other thing I want to show you before I move on is the dust. When there's a lot of dust present, the temperature is low. So dust could be impacting the photosynthesis. It could be impacting the amount of solar energy that is coming into the planet. So this is something that is very likely related. And we can get the dust also from the ice core. See right here, dust is high, temperature's low, dust is high, temperature's low. Now here the temperature's kind of low, but the dust is kind of low. So it's not 100%, but there's enough of a correlation that scientists can determine that there is some sort of relationship. Now, the big problem with climate change is that correlation, great, it is correlated. Look at these, there's peaks, there's valleys, and all the the data is pretty significant. However, we cannot determine causation. Like, we can prove that when CO2 is high, temperature is also high. We can prove that when CO2 is low, temperature is also low. When the dust is high, temperature is low. We can prove that. We can't prove that one causes the other because we were not present 800,000 years ago to take physical samples and to actually measure it with modern equipment. So one of the big problems with climate change is that the climate change deniers are going to argue that this causation, we cannot prove it. Unfortunately, they have a loud voice, and they also have positions in governmental agencies. Some of the climate change deniers are running for office. They're holding, important jobs with fossil fuel companies. It's honestly a bunch of idiots that are making really bad decisions for, not even for my generation, but for your generation. Like, by the time it gets really bad, like, I'm going to be dead. You're going to be still alive. You're going to be suffering in this climate change disaster that is caused by people that are denying this. So, yes, we can prove that they are correlated. No, we can't prove that that it is causing it. However, we are using the scientific method to show relationships, and we are conducting current experiments to show that high levels of carbon dioxide do cause an increase in global temperatures. All right, let's switch gears a little bit. By the way, you can talk to your parents, talk to your grandparents about this. You have watched over 90 videos about things related to environmental science. You do have a good enough background of knowledge that I do hope that you can formulate your own opinion, even if you have some climate change deniers in your life. Okay, positive feedback loop. This is just a review, but remember, a positive feedback loop is a self-perpetuating cycle. We melt the polar ice, which has a very high albedo. We expose ocean waters, which has a low albedo. That absorbs the sun's solar energy and re-radiates it as infrared radiation or heat, causing a warming of ocean waters, and then that melts adjacent polar ice. This is a self-perpetuating cycle, just like the melting of permafrost. When you melt permafrost, it releases methane. That methane has a warming potential 24 times greater than carbon dioxide. So that absorbs a lot of solar energy and re-radiates it as infrared radiation, causing more temperature increase, which melts more permafrost. This is a self-perpetuating cycle. That's why it's a positive feedback loop. Okay, so these changes in global temperatures are impacting the temperature difference between the tropics, which is very warm, and the polar regions, which is very cold. The temperature difference between these two regions are driving our atmospheric circulation. Remember that in the Hadley cells, we have the warm, moist air rising up at the equator, reaching the top area of the troposphere, moving aside, and then dropping again. The cooler, not cold, cooler, dense, dry air falls down to the Earth, or sinks back down to the Earth at 30 degrees north and 30 degrees south latitude. But with this change in, the polar areas are getting warmer, so with this less of a difference between the temperatures, the Hadley cells have the potential to expand and widen, which would then expand the tropics, which would then kind of it would mess up and throw a whole curveball into this atmospheric circulation. So this expanding of the Hadley cells could not only transfer heat to northern and southern latitudes, but it could also allow insect vectors to survive and spread diseases like malaria. Now, this could also have bigger impacts, like, for example, the destabilization of the jet stream. The jet stream is an upper atmosphere or upper troposphere flow of winds. It's basically atmospheric currents, and we ride the jet stream when we fly to Europe. The planes basically go up to cruising altitudes, and the jet stream pushes them along because it is a high altitude atmospheric flow. Now, with the adjusting dimensions of the Hadley cell, it's kind of throwing a loop throwing a curveball into the jet stream, and the jet stream's getting off balance. And with the jet stream off balance, there's going to be times when cold polar air is brought down farther south. If you notice, there's been a lot of, over the last few years, polar vortexes. A polar vortex is when you have this cold polar air and coming and sitting down and just bringing all that cold air down to the continental United States. It's hit New York, where the temperatures will be like 0 degrees, maybe 5 degrees for the high, 10 degrees for the high, and it's incredibly cold. Likewise, you'll see times when parts of, up in the Arctic Circle are very warm. There was times when there was the warmest temperature on record in Siberia, has occurred over the last 10 years. And these temperatures are happening up in northern latitudes, and it's a problem because this is where we have a lot of the permafrost. So if we have areas that are getting warmer that shouldn't be warm, and areas that are not used to being cold, like this disruption has major impacts on the overall climate of the planet. If you look to different areas like New York shouldn't be cold, as cold as they have been, but also there's areas that are very hot and very dry. So parts of New York and the Northeast will be cold and a lot wetter, and there's going to be parts of the West that are going to be warmer and a lot drier. And we have seen this. We've had the summer of 2021 was a very wet summer. We had a lot of moisture. Likewise, the summer of 2021 was a very dry summer for the western half of the United States. So when we have this global climate change, we're not actually saying it's not global warming, because we're actually having some parts of the world are going to get colder and some parts of the world are going to get warmer. So it just means that our overall climate is going to change from what we're used to. Now, with the atmospheric temperatures changing, a lot of the warm atmospheric temperatures, the heat in the atmosphere is transferred to the ocean. And the ocean has a lot of, it can absorb a lot of heat before it actually changes the temperature. But with the ocean getting warmer, you can interfere with this thermohaline circulation. And this is a current of water in the ocean. You have this warm shallow current that goes from the Pacific Northwest down through Australia, through the Indian Ocean, and then up through the North Atlantic, where it becomes colder, and then it sinks down to the bottom, and then you have this cold, deep, salty current. So this current flows around and it transfers nutrients around the planet. Along with it, it also can kind of keep our temperatures a little bit consistent. Now, if you notice here, you have this warm shallow current going along the east coast of the United States and then going up to Europe. So it's warmer air going up to Europe. And I know we talked about this when we were talking about air currents and ocean currents, but typically a lot of Europe is warmer than areas at the same latitude as North America, and that is because of this North Atlantic current. Now, one of the things that's happening in the North Atlantic is we're having ice melt from Greenland, and this ice melt right here is melting this ice, the glaciers that are on Greenland, and this fresh water is entering the Atlantic Ocean. So we're having a lot of fresh water buildup, and fresh water is less dense than salt water. So salt water is what's going to is what's going to sink. Salty, cold water sinks. Warmer, fresh water will float. So when you have the melting of this and you have a lot of buildup of fresh water, the water is not able to sink. So it could be impacting this thermohaline circulation. In fact, it's going to slow down this Gulf Stream water, and instead of warming Northern Europe, which is the standard case, it's going to actually show a cooling of Northern Europe, which is the major problem. Again, Northern Europe will be cooling because of this influx of cold, fresh water into the North Atlantic. So globally, the climate has changed. This is surface temperatures globally, and if you notice, these are the temperature increases, this is the temperature decrease. It's gotten the worst at the poles, like at the North Pole especially, because of these oceanic currents. And you'll also notice right here, this is where Greenland is, and then this is the water. This is because of the cold water that's entering the Atlantic Ocean. So if you notice, the current should go up this way. You have Scandinavia, you have Norway, Sweden, Finland, is actually getting colder because they're not getting that warm water from the North Atlantic to kind of keep their temperatures in check. So now because look at the latitude, they're at a latitude that's up the same as Greenland, the same as like Canada and Alaska. Like, it should be a lot colder in Norway and Sweden. And now with this interruption of the thermohaline circulation, like Norway and Sweden are probably going to be along the same temperatures that they should be at that latitude. However, this is not what they are used to, so this is a drastic change in their climate. Obviously, you see this, the South Pole, Antarctica, is getting colder. But honestly, what you really need to focus on is what's happening up here, because this is what you're going to be asked about in FRQ writing and in multiple choice practice. So on coastlines, when you have this climate change, you're going to have changing ocean currents, and some things that can happen is you have barrier islands like the Rockaways, you have Fire Island, you have the Outer Banks of North Carolina. So these are basically like islands that are like sand dunes between the mainland and the open ocean. And these barrier islands will become damaged because there's going to be a lot more ocean and beach erosion. So the sea level is going to rise, it's going to beat down on these islands, and then eventually parts of these islands can wash away. Now, you could construct seawalls, and this is what they've done up in Northern Europe. This is what they've done in New Orleans. This is what they want to do, things like this. There's been discussion of doing stuff like this in the New York area. However, what this is really doing is just delaying the inevitable. Like, you can build a seawall, but what happens when it rises up and now it's going to breach the seawall? Then you build a taller seawall, What we really need to do is we really need to solve the problem at the core, and we really need to stop releasing carbon dioxide into the atmosphere. We need to break our reliance on fossil fuels, really, is what we need to do. And with this, global climate change is also going to come interruptions to the hydrologic cycle. Warmer temperatures means that water is going to evaporate faster, which means there could be more desertification in areas that are susceptible to that. There's also could be areas that have more rain. So in areas that are drier, you're going to have faster evaporation. In areas that are getting more moisture, you're going to have water erosion. So both of these are not necessarily going to happen at the same place, but they could happen at the same time in different parts of the world. And we've talked about what's going to happen to polar bears, but polar bears live on Arctic sea ice. Polar bears hang out in spaces in the ice. There's little open holes, and that's where the seals will come up to breathe. And when the seals come up, the polar bears attack, and that's one of their major food sources. So without this polar sea ice, the polar bears do not have they do not have a habitat, but B, they also don't have a convenient food source. So a lot of polar bears are now moving to human habitations in like northern Siberia, in the Scandinavian countries, also in parts of Canada and Alaska. If you look, this is the sea ice, and this is the predicted sea ice in 2050. So this is it says 100% of 1955 volume, and then it's only going to be half as much by 2050. So that's a major problem because polar bears are already threatened, and they could definitely become on the verge of extinction in the next 50 years. All right, there was a bunch of information. A lot of it was kind of like making some points and tying some things together that we've already learned. But I want you to look at this map, and this shows temperatures. So I think you can kind of figure that out using this little key. But I want you to explain how the data to the left supports the hypothesis that a cold spell in the Midwest was caused by a destabilized polar jet stream. So I look forward to seeing what you come up with and your responses. I thank you very much for your attention. I hope that this video was informative and not too lengthy. Have a wonderful day. I will see you soon.